is Kevin Gregorio.
Marisol Contreras.
And my name is Andre Silva.
And we're group 20, and for our project we worked on a solar and wind hybrid power system. So this project consisted of us designing and manufacturing a hybrid energy system at a low cost that is easy to operate and has minimal maintenance requirements.
Literature survey is the comparison of our product with the other companies. We have some power calculation and some first product. The daily power generation of our product is 1,500. In comparison to the other one is 850. The voltage produces 18, in comparison to the other one is 17. So the current amps is the average, 4.5. And the use of our products in general, we're gonna use during the day and night. In comparison to the other one, it's gonna be only during the day. And the most important thing is affordable for the customers because the price is approximately $1,750. In comparison to the other one, is $3,500.
So as Marisol just mentioned, there are similar products available in the market. The problem, however, is the cost. We feel that their cost is too high. So in order to stimulate current businesses, we set out to manufacture a portable hybrid power system that contains both solar and wind technologies and is capable of delivering 1,500 watts of continuous power.
So the system is composed by 4 main components. We have the wind generator, the solar panel, the charge controller, and the inverter. And the way that the system works is very simple. You have the wind turbine connected to the solar panel together, going through a charge controller. The charge controller is here just to make sure that the current will flow in one direction from the turbine to the battery. We have our battery bank, and finally we have an inverter, which we convert the current to alternating current, which is the one that we use. And in order for the system to be portable, we had to figure out a way to store all the electric components. And the best idea that we come up with was to adapt a heavy-duty toolbox and turn that into a battery bank. So we have a toolbox here, and as you see, we have 2 deep cycling marine batteries connecting parallel. We have the charge controller and the inverter. And just for safety, we decided to add a very powerful fan to remove the heat during operation.
Here we have a breakdown of the structural components of our tower. You can see the rendering used in SolidWorks and actual pictures of our product. Over there you have the solar panel, as you can see. It was mounted onto the tower using 2 bolts. It was mounted on the lower section of the pole just to reduce the stresses that it's going to be experiencing at high winds. Here we have the pivot system, which consists of a pivot bracket, which is right here. It's so that it can rotate around the tower 360 degrees. We have a slip ring on top that connects the cable of the generator so that when it rotates, it doesn't tangle itself around the tower itself. And the cable would go into the pole and would slip out of the cord grip here and into the electrical power box. Here we have the tail boom and vane, which is an assembly itself. We did it this way in order to maximize storage capacity. So whenever you want to use it, you would just install it onto this bracket which we manufactured using hitch pin. So this product was designed with the idea of it, having an extendable tower, just to clear regions of high turbulence, which may be caused by a nearby tree or wall. So in order to accomplish this, we implemented a gearbox and lead screw system, as you can see here. So as you rotate as you crank the gearbox, we have a stainless steel tube that basically drives up and down, and it drives up the upper half of the tower, to up to 15 feet. Here we have the overall product dimensions. As you can see, when the product is not extended, we have an operating height of 10 feet, but when it's fully extended, we have an operating height of 15 feet. So you have an extension of 5 feet with the use of the gearbox and lead screw. So we did some stress analysis, displacement, and factor of safety calculations. And from that, we learned the following. So from this, we can make the following recommendation, which is basically if you have the tower fully extended at 30 miles per hour, we recommend to put it at its non-extended position because of the stresses the stainless steel is going to be feeding at that point. As you can see here, the factor of safety decreases as wind speeds increase. It's an obvious fact, as well as the stresses increase as wind speeds increases.
Okay, efficiency. It's been determined in the past that the maximum efficiency of any wind turbine is 59.3%, and that's known as the BATS limit. And the reason behind that is that in order for a wind turbine to be 100% efficient, you will have to collect 100% of the kinetic energy available in the wind. And for that to happen, the blades would have to be a solid disc, and of course it wouldn't spin. And we decided to actually calculate the efficiency of our system, and there are a couple of different ways of doing that. The easiest way is comparing the power output of the wind turbine, which we got during an experiment, with the theoretical energy available in the wind. And as you see, this is the final plot of efficiency. For example, our system is more efficient at 13 miles per hour, which is 45%. As you increase the wind speed, you still produce more power, but just not as efficient as the 13 miles per hour point. The 13 miles per hour point only means that at that point, the turbine is doing a better job in converting the energy available in the wind. The efficiency for the solar panel is very easy to be determined. Most manufacturers use this general formula that relates the maximum output of the panel with the heat flux and the area of the collector. It turned out that the efficiency of our system, our solar panel, is 17%, and considering that most solar panels are only 11 to 20% efficient, it seems that it was a good selection. This is how we did our testing. We actually used an air bolt and a wind meter. And the nice thing about the charge controller that we use in our system is that actually tells you the amps and the voltage. So with that data, that's how we found our final plot in the previous graph. I'm sorry, I don't know why the video is crooked, but unfortunately, when you did the testing first, we used a shaft that was like too long, and the wind was actually hitting below the blades. That's why in that video, you don't see the blades spinning too fast. And another day, we did the same testing for lower shaft, and that's how we got data. It was actually facing straight to the wind, and that's how we got like our current and our amps, and we found our power output.
So this is a cost breakdown of our project. As you can see here, the total cost of our hybrid power system was $1,747.52. The major components here were the solar panel, the generator, and the charger controller themselves. They were the ones that cost the most. For all other components, it was assumed that we were going to be producing at max volumes, and we got in contact with local manufacturers, to see what the cost of producing certain parts would be.
And standards. So if we were to actually sell this product, this is the list of standards that we think is a good idea to implement. The first one is the National Electrical Code. It's basically a standard in America for the safe installation of electrical components. The second one is similar with international, and of course, NSI and ISO units will be implemented in the project. And the last one is just nominal pipe size. The standard is in America for pipe selection.
For global learning, we actually designed this product to be manufactured anywhere in the world. We use components that are easy to source anywhere. In addition, we also developed a multilingual user's manual, both in English and Spanish, which includes assembly instructions, operating instructions, maintenance instructions, technical specifications, and safety guidelines. Finally, we also developed manufacturing drawings, were also done using ANSI and ISO drawing standards.
Now we're going to talk about the environmental benefits. So in our product, we use recycled material, especially the plastic compounds and the aluminum. No pollution and no contamination because we're going to use natural resources. And we're going to help to slow and stop the global warming because actually the companies, they produce energy, they have to use wood, coal, oil, and gas. We try to avoid that. And the economical benefit we have is cost effective because we're going to use an expensive material, easy to manufacturing, low cost manufacturing. We're going to stop and reduce the monopolization of the power company. That means is that people are going to have that control about where, how, and when can use the energy. We're gonna build in rural areas and far areas, and especially developing countries, they need energy, and they have to use and increase the life of the standards. The division of responsibility, we are 3 members in our group. We divide the project formulation, research survey, simulation, costing, and final design. The project timeline will start in August, project formulation. So in November, we made a conceptual design. Continue with the process in the February was the important part because we had to testing and analyzing the product. And finally, we are here to show our final design.
So conclusion. So the idea of this whole project was to combine both a wind turbine and solar panel together. So why we did that? The idea of combining both systems is to achieve constant power production, either from the sun, from the wind, or both. We must keep in mind that this system only produces 1,500 watt-hour. For example, this is not enough to power a house. However, this system was not designed to power a house. The system was designed to provide a power solution for remote areas that do not have access to electricity at all. And from that perspective, 1,500 watt-hour can go a long way. And the system is fully functional, safe, and efficient. And unfortunately, the system was too large to bring inside the room. However, we have the system set up outside the FIU and the main entrance facing Flavor. And you are more than welcome to come and take a look. Thank you.
Thank you.
Okay, any comments, questions?
Have you had any long-term testing on this and what the life estimation is of this unit?
Of the whole system? Well, I mean, it would be based on the life of the batteries. Usually, if you can take good care, we designed a system such a way that 1,500 watts is equivalent to only 50% of the battery bank capacity. So if you don't discharge a battery like every day fully to 5 or 10%, you increase the life of the battery. So this system is expected to last 10 years for the batteries. And of course, we will have to replace the batteries, and the system should continue working.
In determining your 1,500 watts, what percentage of that power were you saying was generated from wind versus solar?
Yes.
And what would be required to actually meet that in term for each?
Yeah, that calculation was, we just made an assumption. The assumption was that the system would be used in areas that you have at least 10 miles per hour wind blowing for at least 10 hours a day and 5 hours of strong sunshine. So 5 hours of strong sunshine, that's where we get our 500 watts. And 10 hours of 10 miles per hour wind, that's where we get our 10,000 watts. So the total will be 1,500 watt-hour of the system.
You actually got 500 watts of power from solar panel?
No, the solar panel will be, I mean, we assume that usually you have like 5 hours of strong sun. Solar panel that we use is rated at 100 watt. So you get roughly 500 watt from the watt-hour from the solar panel. You will still produce more along the day, but it's just going to drop as the sun.
What would you say, because you showed a comparison of other competitor units within 3,000 price range. Yours is $1,500.
1,700.
1,700.
Yes.
What would you say was the biggest contributing factor for such a lower price compared to the others?
Well, this is cost to manufacture.
Right.
We're not taking into account, sales cost, sales price.
Right.
Their sales price is not much. So we're not really sure what their cost is.
Right.
This is a way, this project was made so that you can see that you can develop it yourself, or anyone can develop it themselves at a much lower price.
You didn't include labor in your costs?
I did.
You did?
Yes.
Oh, okay.
Yeah, and it seems that this whole idea about combining solar and wind in one single system is technically new.
Right.
We only have a few products in the market, and that's why they have such high price.
Right.
And that was one of the nice things about the project, because we try to encourage new companies to actually design these and prove them that, well, you can actually design these for a lot cheaper.
Right. Because I know solar power is kind of starting to grow the idea behind it, and people are saying, hey, we can do this, and like you said, get rid of the monopoly of the power
Yes.
companies. I'm thinking, well, if it's that much less, why can't they do it? Especially as I'm trying to figure out why yours is less than theirs, you know?
That was the objective of the product. So
Right.
the comparison with another companies is to understand and to, because usually the company is dedicated to technology. The
Right.
objective of our research on that and to improve our product. That was usually in the market we want to find a lot of solar panel. But you don't want to find a solar panel combined with a wind. So that's going to be more effective for product.
And the components, as we move along the years, the components are getting cheaper and cheaper. Today it's technically cheaper to purchase a solar panel. You can get one for $140. That's how much it costs for our panel. And if you actually sit down and add the numbers for each component, you'll figure out it's actually not expensive.
Where'd you get your panels from? I'm just curious. Where'd you buy them from?
Was Regani, we bought an Amazon.
Oh, Amazon, okay.
Yeah.
Yeah, because I noticed Harbor Freight, I see them selling a kit.
Yeah.
So I'm just curious if that was one of those.
Yeah, we
And,
we saw that one after we bought this one.
and the generator that we use is from a company called Missouri Solar and Wind.
Uh-huh.
They are pretty well known for like hybrid system, and it's AC. We decided to go with AC current, and it's very efficient. It's a really good motor. It's basically they call permanent magnet generator, but it's technically an alternator. The only difference, they don't want to call an alternator because they don't want to mix up with a car alternator. The difference is that they actually change the stator port. They put the stator port inside the motor at an angle to facilitate the spin, the blades.
That's why for this generator, it only takes 9 miles per hour of wind to actually start rotating.
Yeah, that's the, before, you need at least 9 miles per hour, you won't produce anything at all. Yeah.
Just curious.
Well, thank you.
So I encourage you guys to go see the project outside.